There we go. All right, so those of you who are showing up, try to find a seat. So this is the second of our 2 lectures this semester, the 4th of 4 for the academic year. So we'd like to thank, of course, our sponsors. Dow has endowed our stockroom a long time ago. Some of our lecture materials are sponsored or, helped through Cengage Learning. And introduce our speaker here. Our speaker comes to us from Rice University. Be polite. She also teaches general chemistry on I guess, what is it, 172?
This class 178.
178, the chemistry of cooking. There's this nice piece of art from the magazine profile that I happened to read about her. And, I was just going to show off a couple of her students' final projects. And, I was thinking to myself, why is it that we don't do this in our class? And I thought, well, then I'd be the size of this building or something if I had to taste every single one of yours. So this is a honey-glazed pork belly bao. Looks good. A reimagined Thanksgiving plate. Deconstructed, is that the right terminology? Right, yeah, okay. And then a modernist shrimp fried rice. I thought that was good. And it's dinner time. You guys getting hungry? Yeah? This one had a really long title. Art-inspired bite of coconut blue cheesecake and tropical wine sauce. It's quite the mouthful, literally and figuratively, right? And then interpretations of a bananas Foster. Feels like something went wrong with the grammar there, but it's all good, right? Okay, so without further ado, I'd like to introduce and give a warm welcome to Dr. Lu here.
I guess, there you go, there's my mic. So thank you so much, Ed, for the introduction, and thank you, Tim, for the invitation to come to Texas A&M. So this is quite surreal for me because, as Ed was saying, I'm from Rice University, and our total undergraduate population is 4,200, right? So my general chemistry class that I teach alongside 1 or 2 other professors is a total enrollment of 450 students. So any given section of my class is only 150 students, which is what I hear about 10% of those who are attending tonight. So seeing this many student faces is really surreal for me. But as Ed was showing on the presentations, I really like my Instagram. I post a lot of photos of my classes, not only general chemistry, but also the chemistry of cooking class, and this is definitely an Insta-worthy moment for me. So I'm going to take a picture of you guys really quickly. All right, yeah, see some posing there. Thank you so much. All right, so I'm wondering where the slides are. If I am, maybe we're still working on it. Okay, no problem. Yeah, no problem. So the chemistry of cooking class was basically a little brainchild of mine in hopes to think of a way to teach general chemistry concepts in a very fun way, right? Because I think a lot of times chemistry is often thought as a dry and difficult subject, and we all kind of fall victim to it when we really listen to a really dry and long and dense science lecture. We lose attention. We don't really understand the connections to our everyday lives. So why not try to introduce general chemistry concepts in a more exciting and relatable way? And so this was the opportunity for me to develop a course that was able to combine my profession of being a chemist. So I got all 3 of my degrees from Rice University, and now I'm teaching there as an instructor at Rice. With my wholehearted hobby and passion of food and cooking, I love baking in particular, right? So this was a unique opportunity for me to really combine everything that I love into one class with my students themselves. So this class itself is 4 years in the running already, and just to tell you a little bit about it as they're trying to work on the slides here. What we do, it's only about 20 students who enroll in the class, not because that's the only number of students who are interested in the class. In fact, it's super oversubscribed. It's just the limitations of the space that we have to teach the class in, because on a weekly basis, we have 2 lectures of the chemistry of cooking, perfect, and with it complements a kitchen session. So we actually conduct kitchen laboratory sessions on a weekly basis to hopefully tie in those chemical concepts that they learn in the lecture now into the kitchen setting. And so what Ed was showing you was the photos were of their final presentation. So it was a total culmination of all of their knowledge expressed into one single dish, which is really cool for them to do, right? To express their understanding of chemistry and their excitement of cooking and food into one beautiful dish that they present to a panel of judges. So here's just a sample of all the Instagram photos that I have up online, so you can follow me, of course, at Lesa Tran Lu there. So if you guys want to browse it while you guys are listening to me, that's perfectly okay. So just to give you a snapshot of what it looks like to be in my class, right? But as I typically conduct my chemistry of cooking class, I always like to start off gauging the baseline of knowledge and confidence of my students. So as a quick survey, so just go ahead and show of hands, how confident do you actually feel in your knowledge in freshman level chemistry? Be honest, be honest. Awesome, I like how Dan and Stephanie are raising their hands. I'm glad you guys are raising their hands, because that brings some comfort to our students. So okay, all right, so very, very few, and that's okay. What about your confidence in chemistry laboratory skills? Okay, a few more hands there. What about kitchen skills? Oh, all right, everyone knows how to use a microwave or maybe boil some water for some ramen, that's wonderful. But come on, about your ability to eat and enjoy food. If you do not raise your hand here, I don't consider yourself as a human being, right? Because everyone enjoys food and cooking to some extent, because we all consume food and enjoy food at the end of the day, right? So this really proves the point of being able to use a really fun and interesting topic that everyone can relate to a really, really dry and difficult lecture known as general chemistry, right? And this is the inspiration of how I teach my classes. I'm a full believer of active and inquiry-based learning, meaning that if you want to get good at something, just like in sports or picking up an instrument, you have to practice it. So the way that I actually teach general chemistry, so what you guys are currently taking right now, are in large classroom sections, totally small compared to you guys, where the students are sitting around tables of 6 to have discussions of those lecture concepts in the lecture period. Right? It's a whole operation, but they really do learn from it because they have the opportunity to practice explaining those concepts with one another. But also we design the class in a way to have them actually walk through the historical steps of arriving at the same chemical theories and theories and laws that the scientists have concluded over centuries, if not many years beyond that, right? Those theories and laws that are summarized in textbooks that you guys are reading right now, they actually walk through it using the scientific method to come to those same conclusions, to build their own knowledge. That's the exact same concept in the chemistry of cooking class, right? To actually build their knowledge in the lecture hall and then move it and translate it into the kitchen setting, where they conduct experiments to learn and really reinforce their understanding of science, and really do enjoy it as a form of art, to be honest there, right? So with respect to this particular topic, we always go back to the dictionary to really make sure that we understand what we're going to be talking about. So if you look into the Oxford dictionaries, chemistry and cooking can be found, right? And chemistry, I like to say to my students, is just the study of stuff, right? All the stuff that surrounds us. Everything around us is made up of matter, and we're going to try to study what that matter is, how they're composed, and how they interact with one another. Cooking, to be honest, is just a way of manipulating that stuff, right? Food is made up of matter, and we're going to try to manipulate that food by adding energy to it or mixing different ingredients with one another. So, as I said, it's a really fun way to understand science and chemistry, but also it helps you think more like a scientist when you want to develop a good recipe, a perfect recipe for something. And that is what goes into the process of the scientific method. Right, so let's pick on some biscuits here that I had my students test out recipes for in order to make the perfect buttermilk biscuit, right? So that's the hypothesis, the question that you want to answer to develop a hypothesis. So obviously you have to go back, eat a lot of biscuits, right, in the name of science, of course. And you develop a hypothesis about how to make the best biscuits. And so perhaps we want to pick on the variable of temperature and how temperature affects the consistency of those biscuits. And so you therefore go into the laboratory in the kitchen, in this case, to test out your hypothesis. You'd use different temperatures of butter, cold, room temperature, or hot, or melted, make your observations, analyze your data, and come to some sort of conclusion so as to develop a model that you can test over and over and over again, right, to make sure that it is true. So you obviously eat some more biscuits, right? And you definitely see that the colder the butter is, the flakier that biscuit becomes, and that's something very ideal, of course. But what happens if you change up the fat source? Or what happens when you change up the flour that you use in your recipe? Those cause different changes that we want to study further. Those are the questions that you want to move forward with to develop the perfect biscuit, right? So when we are dealing with recipes in the kitchen, honestly, you are conducting a chemical reaction. Because at the end of the day, when you really want to understand chemistry or understand what you are cooking, you have to understand what it's made out of and how much of that stuff it is made out of. And lastly, how they interact with each other or how they behave under certain conditions. So when you take a look at a recipe, the first thing that you'll always do is to measure out your ingredients, which, when you really dig down deep, it's counting the number of molecules that you are adding into your chemical reaction, right? And this is kind of a cool thing to think about, that generally speaking, the pros in the kitchen, the professional chefs and bakers, actually measure their ingredients by mass and not by volume. It's because, as we all learn from general chemistry, that the law of conservation of mass is really powerful, right? Volume can change simply by the method that you measure your ingredients at or the conditions in which you measure those ingredients out, but mass is always conserved, as well as the counts of those particles. So when you look at a typical biscuit recipe here, right, even though the ratios of the volumes are quite large, right? Here you're dealing with a 1/4 teaspoon of baking soda, but a whopping 2 cups worth of flour. On a molar basis, right, particle count basis, you actually have fewer starch molecules than your baking soda. And in fact, at the end of the day too, on a scale, they're all quite really similar in the numbers of particles that you're adding into your chemical reaction, which kind of gives you a greater appreciation about how chemical reactions occur. And once you measure those ingredients, then you cook it, right? Which is essentially adding energy as a function of time, which obviously affects the amount of potential energy and kinetic energy in your system that causes changes in the bonding nature of your molecules, the interactions between them, but also how they move, such that at a certain critical temperature, you will achieve what you want out of your cooked product when you started off with a very raw, uncooked product. All right, so tonight I'm going to be using a very good example that we all as Southerners love, right? How do you actually go about making the perfect fried chicken? I probably am guessing that many of you have not eaten dinner yet, so I'm so sorry if this is making you super, super hungry, because it definitely is for me right now. Right, but how do you go about making the perfect fried chicken? So there are a couple of questions that I like to think about when I want to develop a really good recipe for it, right? First off, whether I want to deal with white or dark meat, right? Second off, how do you ensure that your meat is really juicy after you've deep fried it? And then lastly, how do you make sure that it's still crispy and crunchy and golden on the outside, but nice and thoroughly cooked on the inside without it being overcooked, right? Because we all don't like dry, overcooked meat. We want to make sure it's nice and moist inside, but nice and crispy on the outside. So hopefully today we're going to be able to break down some concepts, general chemistry concepts, in order for us to develop some methods to make sure that we can achieve the perfect fried chicken. So in the basic food chemistry world, it turns out that those scientists define the world of chemistry in terms of 4 major food molecules, which are highlighted here, but also conveniently organized by the FDA in nutritional fact labels. So first off are your lipids, right? So your fats in general. Then followed by your carbohydrates, and then your proteins, of course. Water is typically never expressed in nutrition facts because by the experiments that they use to quantify these values, they essentially drive off all the water content. But water is a very important molecule that we'll talk about later today. But then there are, of course, obviously other substances within our food, such as inorganic compounds like sodium or other salts and minerals, or other organic molecules like cholesterol or vitamins or other metabolites and additives that we could add to our food. And so this is a nutritional label fact for Kentucky Fried Chicken's 2 drumsticks on the right-hand side. Original recipe, not extra crispy, right? So one really cool trick that you can actually employ as you go around trying to calculate your caloric intake, as college students you don't have to worry about that right now, maybe as you get older you might, is to be able to predict how many calories are in your food by simply following what we call the 9-4-4 rule. When we look at the nutritional facts label, you just take each of the masses of your fats, carbs, and proteins and multiply them by the factors of 9, 4, and 4 respectively, add them all up to get a good rough estimate of approximately how many calories you would be consuming per serving size of these fried chickens here, right? So by this calculation, it's about 540 calories, actually a lot lower than what I was anticipating when I was looking this up. And if we unhide the nutritional label facts, it's pretty darn close. So this is a pretty good rule of thumb that if you're ever curious that you can follow. But as we said, let's talk about these 4 basic molecules right here: lipids, carbohydrates, proteins, and water. We'll hit upon all 4 of them eventually later this lecture, but we're going to talk about the first 3, because even though we know a little bit about all of those first 3, lipids are fats, carbs are your sugars, and proteins are your meats, as we typically think in terms of food, they actually behave quite similarly and are made and destroyed in similar ways. Right? That lipids, carbohydrates, and proteins are actually really large molecules that are made up of simpler units. So you can think of them as polymers, right, that are constructed chemically by assembling smaller pieces together with respect to one another. So it's following this very, very broad model of monomers assembling into a strand known as a polymer. And every single category here has a different type of monomer or simpler one unit that you're connecting. And the way that your body assembles and breaks apart these big molecules is essentially by the same general process. Okay? So in the forward direction, if you actually want to connect these green pieces together, you undergo what we call a condensation reaction, right? Where you lose a molecule of water when you actually connect those 2 subunits together. But this process is also reversible, such that if you actually add water, you can break those bonds apart. And all 3 types of these macromolecules, these food molecules, follow the exact same process in terms of how you break them apart and how you assemble them in your body. Right? So that's pretty cool. Even though they're all very different in their characteristics, they all follow the same mechanism, essentially, general mechanism of how they're assembled and broken down. So let's go ahead and go through each one of them, right? So lipids are your fats and your oils. We know them very well because they are what we call hydrophobic. They do not interact well with water. But as I said, they are macromolecules made up of a particular type of backbone molecule known as glycerol, and attached to it are what we call fatty acids. And different fats and oils are made by altering the identity and the lengths of these fatty acids here, where generally speaking, fats are referring to what are are lipids that are solid at room temperature, so butter is a good example, as opposed to oils which are found as liquids at room temperature. So your canola oil, for instance, with the exception of coconut oil, if you guys know, right? Coconut oil seems like it's a solid, but once you touch it, it starts melting, right? And all of that is due to how long these fatty acid lengths are, right? As well as maybe any impurities those lipids might contain in their samples. And one really good property that we need to keep track of with respect to fried chicken, of course, are the lipid smoke points. So not to be confused with boiling points, which you may have already talked about with phase transitions, right? Boiling points are the point at which the vapor pressure produced of your liquid equals that of your atmospheric pressure. That's not the same as a smoke point. The smoke point, on the other hand, is the temperature at which your substance actually decomposes and starts smoking, right? And so every single lipid has a particular smoke point that you actually want to keep track of, because you don't want to burn your butter, perhaps, when you're cooking, or else you're going to have a burnt flavor in your chicken. So carbohydrates are next, second food molecule that we want to talk about. Carbohydrates, again, another form of a macromolecule, but in this case, we're dealing with simpler units known as monosaccharides, or simple sugars that you're chemically connecting with one another to make disaccharides, right? So 2-unit sugars, so sucrose is table sugar, lactose is found in your milk, of course. Or you can keep connecting them into broader, bigger networks that have a very relevant applications in our bodies for structural support for our cells and in plants as well, or on the converse side, energy molecules, right? We definitely consume sugar and lactose for our energy source. Right? Another cool thing that, historically speaking, is that carbohydrates, as the name suggests, were historically thought of to be hydrates of carbon substances, because they all share more or less a common chemical formula of having one carbon atom shared with every water molecule. But that actually is very deceiving in how these carbohydrates actually exist. So clearly you see that you don't actually observe a carbon atom attached to a water molecule everywhere you look in these structures. It just happens to be that the chemical formula is found in this wonderful ratio. But as opposed to your lipids, your carbohydrates are very water soluble and or hygroscopic, meaning that they absorb water quite well. Next up, your proteins, right? Proteins are really important when we talk about fried chicken. Proteins are made up of amino acids. Those are your monomers there that you're trying to build larger scale molecules with. There are over 500 amino acids that exist in nature, but only 20 of them are commonly expressed or exclusively expressed in our bodies and commonly found in the environment. So these are the 20 over here, and depending on their structure, they have different types of properties in terms of charges and dipole moments, right? And generally speaking, proteins are quite water soluble unless you change something about its structure. And it turns out that proteins are very, very dependent on the structure that they are built, in which that they are built, right? Their 3D structure. Their function really does depend on the structure in which they exist. And if you change anything about the structure by exposing it to different external conditions, and you change the structure, you therefore change the function. And that process is known as denaturation, right? If you expose proteins to excess heat or extreme pH conditions or extreme salt concentrations, for instance, you will change the structure and therefore you will change the function. So denaturation actually is a really common thing seen in the kitchen. The majority of cooking revolves around the denaturation of proteins. And a really good example is cooking an egg multiple ways. As I said, what we're seeing is that we're starting at a raw state, and when you expose it to extreme heat, mechanical stress, even a change in pH, or the storage of them in just a salt tray, you therefore change not only the structure but also the functionality of the proteins found in eggs. Right, such that when you look deep down, these proteins are just strands of those amino acids all coiled up in a very particular fashion, but when you are exposing it to the elements, right, external extreme conditions, you're denaturing them, effectively unfolding those proteins, and if you just let those unfolded proteins interact on their own by intermolecular forces, then you start aggregating those protein strands, creating this mesh network, which is very indicative of cooked protein, right? And so largely speaking, denaturation is very reversible because of the amount of strength within the intermolecular forces that are caused or occurring in the aggregation effect, right? But the take-home message is that the more the more you actually expose your proteins to these extreme conditions, or the longer you expose them to these conditions, the more denaturation occurs for your proteins. Okay, so this is trying to get back to my active learning method because I'm so not used to lecturing all the time. So let's go ahead and have you guys talk about this. Okay, so these are two experiments that we do in the chemistry of cooking class, where we make homemade ricotta by simply taking whole milk and exposing it to acid solutions, right? So there's lemon juice, there's buttermilk and vinegar, and depending on the type, you definitely see changes in the texture. So this is really soft, this is pretty darn hard, this is kind of in the middle, kind of mushy, but also has some structure to it, right? So clearly you should see some sort of dependence on the pH of these solutions to the overall texture of the ricotta cheese. Conversely, a second experiment that we do is to form beef patties, so burger beef patties, right? And depending on when we introduce table salt into the process, whether we add salt to the meat before you grind it and let that meat sit with that salt for a very long time before you form the patty and cook it, or right after you grind it, so a little less time with it, and then finally right before you actually cook the patty, you get 3 different textures here. So take a moment, talk to your neighbors, try to match which one's which. So let's go ahead and see what you guys think. Any brave soul want to answer on behalf of the entire class? If I can see you guys. So let's talk about the ricotta cheese. Which one do you think is a buttermilk? Yeah. The bottom one. Why do you think that?
The way it works is normally most similar to that texture.
Yeah. Yeah, and then your neighbor? Yeah.
The buttermilk has the acid, so that's why.
That's right, yeah. So of the 3 acid sources, probably buttermilk is the most mild, right? When you taste buttermilk, it's not as harsh and as strong as lemon juice or vinegar. And so as we said, the more extreme the pH conditions, the more denaturation we should observe. So with buttermilk being the mildest acid in this series, that will give us the least amount of aggregation that we should see and the hardening of the cheese. So let's go ahead and make sure. So there you go, right? Buttermilk's down below. Vinegar, so it's kind of hard to determine the difference between vinegar and lemon juice, but hopefully you could see, can someone answer this question, because of this experiment, which one should have a lower pH? Which one is more acidic? Raise your hands. I want to see somebody. Come on, come on, come on. Someone try. Oh man, no one actually wants to do it. Oh, in the back. Yeah, vinegar, right? Because it's the harder one, right? It's more dense. There you go. And what about the patties? So, which one has sat with salt the longest? Over there. Oh, do you think this one? Actually, it's not, right? It's okay. It's okay. Can someone help him out? Yeah. Why the top one?
Because it's the most condensed.
It's the most condensed one, right? So the longer it sits with salt, the more it has time to kind of compact and interact with each other, right? So it turns out that it's all in the perfect order as we described down below, happening between your protein molecules. All right, so now finally we can get to the first question, right? Can we choose between white or dark meat? That all depends on what type of proteins we are dealing with meat. And there's one that we want to focus on with regards to the color of the meat, which is known as myoglobin. Myoglobin is a really large protein that has an iron ion metal ion in the center of it, so right here, that's caught within this heme structure that is responsible for the storage of oxygen molecules in our muscles. Right? And it's not only oxygen that could attach a bond with that central iron atom, but other small molecules as well. And depending on the conditions too, the oxidation state of that central iron atom can change as well, right? From left to right, it's getting oxidized. So depending on what is bonded to that central metal atom or ion, in this myoglobin protein, you actually generate a different color. So when there's oxygen attached to that iron center, it creates that pigment very red. If it's just water, but no air exposure to this protein, it turns blue. But as you either cook or expose your meat to oxygen over a long period of time, you're starting to oxidize that metal center, and therefore it creates a brown hue in cooked meats or spoiled meats, in fact. And then lastly, hams or any cured meat indicates that there's some sort of nitric oxide compound that is attached to that metal center, which yields a very pink hue. Right? So depending on how much myoglobin you have in your muscles creates a different color of the muscle, which gets into the idea of what is white versus dark meat. So it turns out that there are two different classifications of muscles that you can consider, depending on how much and how you use those muscles. So white meat is made up of what we call fast twitch fibers. Fibers that are used for quick bursts of movement. So think about a sprinter that only has to run short distances and only short distances occasionally. Right? So if it's only very little movement, it's not really necessary for those muscles to have a continual storage and supply of oxygen molecules, so therefore it shouldn't have a lot of myoglobin in it. And that's why white meat tends to be lighter in color, because there are fewer myoglobin molecules or proteins in that muscle. But of course it's healthier because it has a lower fat content, but it also has a lower nutrient content of other minerals and small molecules. On the other hand, dark meat, so think about how these chickens behave, these domesticated chickens, right? They don't use their wings all that much. They don't fly much in farms. Rather, they stand on their legs and run all day, right? So it requires muscles that can endure high performance, long performance conditions, which means that they require more oxygen, and so therefore require more myoglobin in their muscles. And so they have a darker hue to them. So honestly, at the end of the day, it all depends on your taste, right? Whether you want to eat a little healthier with a lower fat content, but you kind of take away from the tastiness, from the fat content and the nutrient content and the myoglobin content, which does actually have a taste to it from the dark meat. Okay, so to each his or her own when choosing what type of meat you want to cook with, which gets us to the second question. Well, we've already checked out the first question. Let's talk about the second question. How do you make sure that you achieve juicy, flavorful chicken? And in cooking, we use a method known as brining. So we're going to talk about the concepts behind brining, so that at the very end I'll give you some tips of how to achieve good brining to get a good chicken. All right, so brining has everything to do with diffusion. Right? Diffusion, as we know, is the spontaneous movement of molecules from an area of greater to lower concentration, because, as the kinetic microtheory states, all particles above absolute zero should have some amount of kinetic energy by which they move. Right? And there's this natural phenomenon for particles, if they're concentrated on one side, to kind of diffuse across the space over to the lower area of concentration until you have a homogeneous distribution of your molecules or particles that you're observing. So good examples are whether you're dropping salt to dissolve in water or dye drops into water. You definitely see it kind of dispersing over time. That's a natural process, spontaneous process. Same thing with any fragrance that you open up in this auditorium. Over time, the other person sitting up very top there will eventually smell it because those scent molecules are eventually going to travel from an area of high concentration all the way to a low concentration, right? Water is not an exception to this rule, and water, as we know, is the last of the 4 food molecules that we have yet to describe. And water, I say, is arguably the most important food molecule of them all because it has very, very peculiar properties to them. Not only are they small, right, definitely small compared to the other food molecules, but they are really nice and polar and very peculiarly shaped so as to allow for optimal hydrogen bonding between the molecules, right? And this results in a lot of cool properties about water where, you know, for instance, because of hydrogen bonding, that's why ice actually expands and is less dense than liquid water. That's why water requires a lot of heat to evaporate and to boil off, because they have to overcome, or you have to overcome all of those interactions that they undergo. And lastly, because of their polarity, they're really great solvents. They have the ability to dissolve things into them, which gets into the concept of diffusion and another concept known as osmosis, right? Water is so prevalent in our bodies and in all biological systems that it's essentially the dominant medium through which other particles can diffuse, right? And also water will diffuse as well. So when you think about osmosis, which I'm sure you guys have heard about as well, osmosis is just simply observing the spontaneous movement of water. You can think of it in 2 ways. Of water going from an area of high to low water concentration, or from a low to high solute concentration. So solutes are what are dissolved in your water, right? So that is what is going to happen net-wise initially here, right? That eventually this side of this container will lose volume and eventually enter the right-hand side because this is a spontaneous process. So the net movement of water goes from left to right until what we call dynamic equilibrium is achieved between the 2 rates of water movement from left to right and right to left are equal to one another, right? And that creates an osmotic pressure. So now here's your next question to think about and mull over. Now that we know what brining is, essentially what brining is that you're taking a saltwater solution and dunking a chicken breast or thigh into it, right? And we know that the chicken itself is protein, and so we're now exposing it to salts as well as water molecules on its surface. So quickly, what do you guys think? When chicken is added to a brine, in which direction should the water and salt ions move? You guys can chat, no problem. So let's go ahead and see what you guys think. Hopefully, through some short conversations there, you're able to figure out that both of them should enter the chicken, right? Because when you think of it, with respect to water, you're going from a high to low water concentration when you're entering the protein itself, because there's not much water in your protein or your meat, right? And this is osmosis happening from a low to high solute concentration. Solute meaning proteins included. On the other hand, sodium chloride, your salt in your solution, your brine solution, is moving from a high to low concentration. So this is an example of diffusion. So brining is just simply the process of soaking meat in in a salted water, right? And we already talked about how salt is a way to denature your proteins. And so that essentially and effectively opens up those proteins on the surface, making them essentially behave like sponges. Right? It allows them to hold more water, but also reshapes and tenderizes that meat because it opens up the structures. So as we said, water is retained but due to osmosis, but also more flavor molecules and ions are retained due to diffusion. Right? So all of these concepts are really important when you think about brining your chicken for your fried chicken. So how do you properly brine a chicken when you go back into your kitchens and want to make it for yourselves? Right, first off, you want to make sure that the concentration of your brine is ideal, between 5 to 8%, because if you undershoot it, that means that you have a lot more water in your brine than not, which means a lot more water can absorb compared to your salt ions, which leaves you with a very bland chicken. It's just a sponge full of water. On the other hand, if you oversalt your brine to really high concentrations, let's say like 35% of salt, osmosis is going to happen the opposite way, where water is going to exit the chicken and into the brine, leaving you with less water in your chicken, so when you cook it, it becomes drier. The next thing that we're going to deal with is talk about how you can use buttermilk instead of water in your brine, because buttermilk, as we already talked about, is kind of acidic, which helps with the process of opening up opening up those proteins and making it more tender as well, which leads to a more ideal chicken. And lastly, there's some brine recipes that require you to cook some vegetables like carrots and onions and celery to develop more flavors and add to your brine. It could take up to 30 minutes to prepare all of those aromatics. Don't bother with it, because at the end of the day, those flavor molecules coming from those vegetables are pretty large. And so when you think of it, large molecules have a more difficult time going into the protein structure of your meat. And you're not going to let those chicken breasts sit for that long, right? Long enough for salt molecules to traverse a few millimeters into your meat. Any longer than that, you start actually degrading your protein, especially if you were to use buttermilk or any acidic source that could break down the protein at the end of the day. The cool thing is that you could use these same concepts to round out your meal. So any sides that you might be interested in, such as coleslaw, right? Coleslaw, the way that you effectively make coleslaw is to salt your vegetables first, so that you could draw some of its moisture out, rinse it off of that extra salt, and then dump it into your dressing so that your vegetables can now reabsorb moisture in the form of dressing, so you're making it a much more flavorful coleslaw. If you don't do this and you just dump fresh vegetables into your dressing, over time you get really soggy coleslaw. Nobody likes soggy coleslaw, right? So that's where it comes from, that it's a process of diffusion and osmosis. Quick pickles, also the same concepts there. It's by simply immersing your fresh vegetables and your produce into acidic brines. It's a great way to preserve, not necessarily ferment, right, because fermentation is a different process, to preserve your produce, but make sure that you trim off the edges or ends of your fruits and vegetables, because there's some enzymes at those tips of vegetables and fruits that can break down the carbohydrates that make up your produce. And lastly, the process known as maceration. Maceration is just simply covering fruits and vegetables and herbs in sugar so as to draw out moisture from your fruits and vegetables and the flavor compounds of your fruits and vegetables to make a very concentrated syrup. So when you think of a strawberry shortcake and that nice drizzle of fresh strawberries with sauce on it, that's made from maceration. Or if you want to make a really nice limeade, as my students have done in the past, where they just soak a lot, or actually bury in their sugar bags slices of cucumbers and mint and jalapeno for those more bold students, and create a syrup of it that you add to your limeades and your lemonades to enjoy with your fried chicken. So third question now, right? How to achieve a crispy golden texture. That's all about the process of dredging. So dredging, right, deals with flours and starches. So that's definitely a form of carbohydrates for the most part. Flours and starches are just essentially ground powders of different grains or roots. But where starches are basically just made of starch molecules, where they're hygroscopic, flours, beyond the starch, actually has a significant amount of protein in it, which is kind of weird for us everyday thinkers to think about. right? And flours are therefore categorized as either hard or soft depending on how much protein they have. The more protein it has, the harder the flour is. And it becomes really important because remember, those proteins give structure and body to our foods because it forms what we call gluten. So gluten, as what we've all pretty much heard in our lives nowadays, a lot of people have aversions or sensitivities or allergies against gluten so that they might actually have to deal with a gluten-free diet, has everything to do with their sensitivity to process a protein known as gliadins, right? And it can interact with another form of proteins known as glutenins in flour. And when you add water to your flour, those proteins can interact, and with mechanical manipulation through kneading, you can cause these networks to be formed, and that's what gluten is. And the more you mechanically manipulate it, the more kneading you do, the more stretched out and the stronger and more elastic that gluten network is. So this is a cool electron microscope image of what gluten actually looks like on a micro level scale. Right, so when you talk about dredging then, dredging is all about the process of coating your marinated brine chicken with a dry ingredient like flour. But the problem is that all-purpose flour has a significant amount of protein in it, which actually makes the breading really dense. And we don't really want dense breading. We want it to be kind of light. So one solution is to actually offset it with a little bit of cornstarch, which is pure starch, to give it a little lighter, crisper texture. We'll add some flavorants to it, salt and spices, but also add some baking powder. Right? So we'll talk about these two things really quickly. So adding buttermilk to your dredge gives those really attractive crunchy bits that are attached to the surface of your chicken, but also baking powder, as we'll talk about in the next few slides, has a really great application to making sure that your dredging and your batter becomes really nice and crunchy, but also browned, that nice golden brown that we want to achieve, because baking powder is slightly basic, right? It's a weak base. So we have to think about what baking powder is made up of, right? Double acting powder, which is now very common in our kitchens nowadays, are made up of not only sodium bicarbonate, which is a weak base, a baking soda, but also two forms of weak acids, as well as predominantly the amount of cornstarch, so it's just serving as a filler there. And when you hydrate, so when you add water and heat up your baking powder, as in when you bake your cakes, you perform an acid-base neutralization reaction between sodium bicarbonate and the protons that are donated by either of the two weak acids above. And in the process of doing so, you create carbon dioxide gas. And those bubbles, those microscopic bubbles, are what produces the crisp, light airiness to cakes, breads, and also breading for your chicken. Baking powder as a weak base as well helps catalyze a process known as the Maillard reaction, a very, very complicated organic process where at the very beginning it starts off with a reaction between sugar and protein, which is exactly what we have in flour, as what we've already talked about. And through a series of steps and a lot of product formation, you achieve really small molecules, a whole range of molecules, that bring about the characteristic flavors of caramelization and brown bread, all the baked goods smells that we love to smell in the kitchen. All of that are due to the Maillard reactions. And it turns out that by adding baking powder, you increase the pH, which helps speeds up the first step as well as the third step of this process. So baking powder has two purposes the dredge mixture. But now, finally, we have to talk about how you actually cook it all really quickly. So deep frying is a process of adding your chicken, your dredged chicken, into a bath of hot oil. Make sure that you choose an oil that has a high smoke point because you don't want to decompose your fat source before you cook your chicken fully. It therefore achieves a nice, even cooking on the food's exterior, but doesn't guarantee whether the heat can successfully transfer into the interior of your fried chicken, which is a challenge that many cooks deal with. And just as a side note, air fryers are a big trend these days of purchasing really cheap air fryers on your counter. All it really is just heating air as opposed to oil. So yes, it's healthier because you use less oil, but it takes a little longer because air doesn't heat up as readily and as efficiently as oil. So how do we address the third question, right? To achieve that crispy texture, make sure that you add cornstarch and baking powder into your dredging mixer. But as I said, the last problem that a lot of cooks deal with is having unevenly cooked chicken, right? It may look very, very nice and golden brown and crispy on top, but it might be actually raw on the inside. So how do cooks circumvent the problem? Well, they actually deal with frying chicken in 2 steps rather than 1. So some cooks believe in frying the chicken at a high temperature until the outside looks pretty good, and then they take that chicken and put it inside an oven to finish it out at a lower temperature so that overall the chicken can cook evenly until the target temperature is reached, so that meat is safe to consume. Right, so as to prevent in any way the possibility of overcooking your meat to make it dry. Another way is to basically use what we use in a chemistry lab, right? A water bath, to kind of par cook the chicken to reach a food safe temperature. And then once you achieve that par cooked chicken, you therefore dredge it, coat it in that flour, and dump it into the fryer, just long enough so as for that fryer to make it nice and golden brown. Right? And this company who makes the Joule, the immersion circulator apparatus here, believes in their process so much that they coined the recipe as a very appropriate title, right? So with that, I hope that you guys have learned how to achieve the perfect fried chicken. If you guys are interested in learning more about the chemistry of cooking, I highly recommend this book, The Food Lab, from which I took a lot of inspiration for this lecture. But I hope you guys enjoyed this lecture as well as now appreciate science as much as you do with food and cooking. Thank you so much, and I'll see you guys later.